Now in this seventh class, we have to study the next topic. It is polarization. You know that light waves are electromagnetic waves. See, they travels in the form of wave. In the light waves, electric and magnetic vectors vary sinusoidally such that their vibrations are perpendicular to each other. See here, this is, assume that magnetic vector and this is electric vector. So their vibrations are perpendicular to each other. One is in this direction, another one is in this direction. Also, they are perpendicular to the direction in which they propagates. So the vibrations are perpendicular to the direction in which they propagates. They are in two perpendicular planes. One is magnetic wave is in this plane, electric wave is in this plane. So ordinary light has got vibrations in all directions. And if the light has got vibrations in all directions, that light is called as unpolarized light. So it has got in this direction, here, in all directions, it has got vibrations. For the sake of convenience, we are considering only two vibrations perpendicular to each other. So this is one vibration parallel to the board, and this is another vibrations perpendicular to the board. When such unpolarized light, if it has got vibrations in all directions, it is called as unpolarized light. When such unpolarized light is allowed to fall on this tourmaline crystal, so tourmaline crystal has got one axis, that axis is a transparent, and all these things are opaque to light, cannot pass through this. Then only those vibrations which are parallel to this axis will pass. Then it has got vibrations in only one plane. So such light is called as plane polarized light. If the light has got vibrations in only one plane or confined to a single plane, this light is called as plane polarized light. Then consider this is tourmaline crystal 1. Here all these things are opaque medium, only one axis, it is called as crystallographic axis. If you go on observing that light by rotating this crystal through 360 degree, no change in the intensity of the light is observed. Because if it is in this direction, say one vibrations may transfer. And if you rotate this slightly, one stops, two vibrations may pass. Like this, if you go on rotating this single crystal in through 360 degree, then no change in the intensity of the light is observed. This is called as crystal T1 is called as a polarizer. And whether the light coming out from the polarizer is plane polarized or not can be checked by another tourmaline crystal T2. It is called as analyzer. So assume that two axes are parallel. Then intensity of the light coming out from one crystal will also pass through another crystal. No change in the intensity of the light. Then if you go on rotating this analyzer, slowly intensity of the light goes on decreasing, and when this axis of the analyzer become perpendicular to the axis of polarizer, light is completely extinguished. That means intensity of the light is zero. If you go on rotating this further, slowly intensity of the light goes on increasing, and it becomes a maximum when this again axes are parallel. So for 360-degree rotation of this analyzer, 2 times it is maximum and 2 times it is minimum. If the light is vibrations are confined to a single plane, that light is called as a plane polarized. Then this plane polarized light can be represented in the diagram by this figure. If you are drawing in the figure showing the arrow mark vibrations parallel to the paper or parallel to the board, then such vibrations are called as plane polarized light with the vibrations parallel to the board. Then observe another figure. If you are showing this dotted lines, this is also plane polarized light, but the vibrations are perpendicular to the board. So what is polarization? If the light vibrations are confined to a single plane after passing through the tourmaline crystal, it is called as plane polarized light, and the phenomena of confining the vibrations to a single plane is called as polarization. So here in the figure, tourmaline crystal T1 is called as polarizer and T2 is called as analyzer. Now next we have to study what is Malus law. This Malus is the name of the scientist. He showed that how intensity of the light coming out from this analyzer varies with its angle made by its plane with the plane of the polarizer. That means if these two are parallel, then intensity of the light coming out is maximum. If the planes of these crystals goes on changing, intensity of the light goes on changing. He showed that how the intensity of the light coming out from the analyzer varies with the angle made by its plane with the axis of the polarizer. According to Malus, the intensity of the light coming out from the plane of the analyzer is directly proportional to square of the cosine of the angle between the axis of the analyzer and the polarizer, or the plane of the polarizer and analyzer. Then assume that this is the completely plane polarized light is incident on the axis of the analyzer. A is its amplitude of the light. This amplitude can be resolved into two components. One is A cos theta, because theta is the angle between plane of the polarizer and the plane of the analyzer, and another one is A sin theta perpendicular to the plane of the analyzer. Then this A can be resolved into two components. A cos theta along the plane of the analyzer, A sin theta perpendicular to the plane of the analyzer. We are not interested along the perpendicular direction because no light goes along that direction, only it passes through the analyzer. Then according to the smallest law, it is intensity of the light coming out is a square cos square theta. So what is a square? Here a square is equal to I, nothing but intensity of the plane polarized light which passes through the polarizer. Therefore, this is I theta is equal to I cos square theta. This is your Malasana law. Then we have to discuss special cases depending on this theta. What is this theta? Theta is the angle made by plane of the polarizer and the plane of the analyzer. So if your theta is 0 or 180 degree, if the angle theta is 0 or 180 degree, means assume that this is polarizer and this is analyzer. 0 means they are parallel, 180 degree means in this direction. So theta is 0 means cos 0 is 1, 180 means it is 1. Therefore I theta is equal to I. So light has got a maximum intensity when theta is 0 or theta is 180 degree. Then another case, if theta is 90 degree, if theta is 90 degree, means what? Both the axes are perpendiculars. Plane of the polarizer and the plane of the analyzer is perpendicular. Then in this case, I theta is 0. Intensity of the light coming out from the analyzer is 0. Now let us study polarization by double refraction, or it is by reflectances. When an ordinary light or unpolarized light is incident on a certain crystals like that of calcite or quartz, the incident beam suddenly split up into two. This phenomenon is called as double refraction. Then one of the beam follow the laws of refraction. This is called as ordinary ray. It lies in the plane of incidence. Then another ray does not obey the laws of refraction. It is called as extraordinary ray. Both the beams are plane polarized with their plane of vibrations are perpendicular. Then there is one particular direction along which if the ray incident, you will not find ordinary ray and extraordinary. That means double refraction is not possible. So this direction is called as optic axis of the crystal. Then why this double refraction takes place? So on falling on the crystal, the velocity of the ordinary ray remains constant. Therefore, its refractive index also constant. Then the velocity of the extraordinary depends on the angle of incidence. The refractive index of this extraordinary ray is not constant. This crystal in this case is called as doubly refracting crystal. Then if you take a doubly refracting crystal and place it on the table, you can find the two images. One corresponds to the ordinary ray, another corresponds to the extraordinary ray. If you go on rotating this crystal, the position of the ordinary ray remains constant, it does not changes, but the extraordinary ray describes the circle. This is about the polarization by double refraction. Now we should know what are uniaxle crystal. If a doubly refracting crystal has got only one axis, only one optic axis, such crystals are called as uniaxle crystals. Example is quartz crystal and calcite crystal. These uniaxle crystals are of two types. One is positive crystal and another one is negative crystal. What is positive crystal and what is a negative crystal? If the velocity of the ordinary ray is more than the velocity of the extraordinary ray inside the doubly refracting crystal. In other words, if the ordinary ray travels faster than the extraordinary ray inside the doubly refracting crystal, such a crystal is called as positive crystal. Example is quartz is the positive crystal. And what is a negative crystal? If the velocity of the extraordinary ray, or in other words, if extraordinary ray travels faster than the ordinary ray inside the doubly refracting crystal, it is called as negative crystal. Then inside this crystal, velocity of the ordinary ray remains constant, whereas velocity of the extraordinary ray depends on the angle of incidence. So if the angle of incidence or direction changes, velocity of the extraordinary ray changes, but velocity of the ordinary ray does not change. Then in the positive crystal, the maximum velocity of the extraordinary ray is along the optic axis. So along the optic axis, extraordinary ray travels with the maximum speed. So perpendicular to the direction of the optic axis, it travels with the minimum speed. Then in a negative crystal, the extraordinary ray travels slower, means it has got a minimum velocity along the optic axis and it has got a maximum velocity perpendicular to the optic axis. Then along this optic axis, you know this here also, velocity of the ordinary ray is equal to velocity of the extraordinary ray. Here also, velocity of the ordinary ray is equal to velocity of the extraordinary ray inside the crystal. But what about the refractive index? Refractive index of the ordinary ray is less than refractive index of the extraordinary ray. in positive crystal. In negative crystal, it is reversed. Velocity of the ordinary ray is greater than velocity of the extraordinary ray. So, example of negative crystal is calcite, and example of positive crystal is quartz. And if an unpolarized light or light is incident on the doubly refracting crystal, each points inside the crystal acts as the secondary sources. They sense the wavefront. One is two wavefront, one is for ordinary ray, another is for extraordinary ray. Then always, in the case of positive crystal, the wavefront of the ordinary ray lies outside the wavefront of the extraordinary. This is extraordinary ray and this is ordinary. From this it is clear that the ordinary ray describes a circle because it travels with the same speed, whereas for an extraordinary ray, wavefront is ellipsoid because it travels with a different speed. Then in the case of negative crystal, the wavefront of the extraordinary ray lies outside the wavefront of the ordinary. This is for extraordinary ray and this is for ordinary ray. Now, what is Heisens theory of double refraction? Heisen has explained the double refraction phenomena by extending his theory of secondary wavelets in a suitable manner. According to this Heisens theory, when a wavefront is incident on the doubly refracting crystal, each point in the crystal acts as the source of two wavefronts. One wavefront corresponds is known as ordinary wavefront and another wavefront is known as extraordinary wavefront. Ordinary wavefront corresponds to the ordinary ray. Extraordinary wavefront corresponds to the extraordinary ray. In the case of this positive crystal, the ordinary ray travels with the same velocity in all directions. In the case of negative crystal also, ordinary ray travels with the same velocity. Its refractive index is constant. Therefore, it describes a spherical wavefront. Velocity is same. Whereas the velocity of the extraordinary ray changes with the direction, it describes an ellipsoid with the revolution. This ordinary wavefront and extraordinary wavefront touch at a point on the axis because along the optic axis there is no double refraction. So velocity of the ordinary ray is same as velocity of the extraordinary ray. In the case of positive crystal, this ordinary wavefront lies outside the extraordinary wavefront. In the case of negative crystal, it is different. This inside this ellipsoid or inside the extraordinary wavefront, ordinary wavefront lies as a circle. So this is about the Heisens theory of double refraction. Only when the wavefront is incident at a point on any doubly refracting crystal, each point on the doubly refracting crystal acts as the source of two wavefront. One wavefront is called as ordinary wavefront, another wavefront is called as extraordinary wavefront. Ordinary wavefront corresponds to the ordinary ray and extraordinary wavefront corresponds to the extraordinary ray. Now, what is Heisens theory of double refraction? Heisen has explained the double refraction phenomena by extending his theory of secondary wavelets in a suitable manner. According to this Heisen theory, when a wavefront is incident on the doubly refracting crystal, each point in the crystal acts as the source of two wavefronts. One wavefront is known as ordinary wavefront and another wavefront is known as extraordinary wavefront. Ordinary wavefront corresponds to the ordinary ray. Extraordinary wavefront corresponds to the extraordinary ray. In the case of this positive crystal, the ordinary ray travels with the same velocity in all directions. In the case of negative crystal also, ordinary ray travels with the same velocity. Its refractive index is constant. Therefore, it describes a spherical wavefront. Velocity is same. Whereas the velocity of the extraordinary ray changes with the direction, it describes an ellipsoid with the revolution. This ordinary wavefront and extraordinary wavefront touch at a point on the axis, because along the optic axis there is no double refraction. So velocity of the ordinary ray is same as velocity of the extraordinary ray. In the case of positive crystal, this ordinary wavefront lies outside the extraordinary wavefront. In the case of negative crystal, it is different. This inside this ellipsoid or inside the extraordinary wavefront, ordinary wavefront lies as a circle. So this is about the Heisens theory of double refraction. Only when the wavefront is incident at a point on any doubly refracting crystal, each point on the doubly refracting crystal acts as the source of two wavefront. One wavefront is called as ordinary wavefront, another wavefront is called as extraordinary wavefront. Ordinary wavefront corresponds to the ordinary ray and extraordinary wavefront corresponds to the extraordinary ray.